in this video. What I mean by that is we are going to look at some situations, real-world situations, and see how we can use quadratic functions to model them and solve for different scenarios. So let's get started. Our objectives are to write quadratic functions modeling real-life applications and use them to solve problems, to use technology and model linear and quadratic functions so that we can make predictions, and to determine the equation of a parabola when given points on that parabola. So let's get started. Here's our first example. In this first example, Philip plans to construct a dog pen off the back of his garage, using its back wall as one side of the pen and constructing the rest of the rectangular pen from 28 feet of fencing. We want to determine the maximum area of the pen and its corresponding dimensions. So when working with these type of problems, the first thing you want to do is draw a picture. And so what that looks like is you have a wall, that's the back of the garage, and then you have your three other sides. Those blue sides represent the fencing, and he has 28 feet of fencing in total. So if you let the width be x, both of these sides would be x, and so that would leave you 28 minus those 2x distances of fencing left for your length. Does that make sense? You would have 28 in total, but take away those two widths, which are x long. Now with that picture, we can start to write a function that will model the area of the rectangle. Well, the area of a rectangle is just your length times your width. So that's 28 minus 2x times your width, which is x. A little bit of distribution will give you the following. And I'm just going to rearrange this so that it is in kind of more of a standard form from the highest, largest exponent to the least. So that is our area. And if you were to graph that function, it would look something like this. And remember, so what you're looking at is the x value is the width. So if you're looking at your x-axis, you can see that depending on how wide it is, you'll have a different area. Okay, so we're looking for the maximum area, and that's the maximum on your graph. So since your vertex, that turning point up at the top, is your maximum, we need to find its coordinates, the h and k. All right, so that's opposite of b over 2a. Our b value is 28, so make it opposite, divided by 2 times negative 2. That's going to give us 7. So our maximum width is 7 feet. That's what we're going to work with. And that will give us an area. If you plug in 7 for your width for your x value, you'll have an area of 98. And that would actually be square feet. So let's interpret what this all is telling us. We're going to have a maximum area of 98 square feet, and it's going to be obtained when our pin for our puppy is 7 feet wide. And to find that 14, you take 28 minus 2 times 7. That's 28 minus 14, which is 14. So we've answered both parts of our question. And now we can move on to another example. All right, now we're working with a cost analysis type problem. A flight between two cities averages 81 passengers when the airline charges $210. This airline estimates that it will lose one passenger for every $3 fare increase. what is the maximum revenue generated by this flight, and how much should the airline charge to achieve this revenue? So we're trying to help the airline figure out, okay, what would be an appropriate amount to charge so that they can earn their maximum amount but also not lose too many passengers, because as you bump up the cost, less people want to fly. So we're going to begin by assigning a variable to our key unknown and then express all the others in terms of that variable. We'll let that variable be x, and x is going to represent the number of $3 increases. That'll help us know their total cost, and it also helps us to know how many passengers. So their price per passenger, is 210 plus $3 times the number of fare increases. So that also means that 81 minus the number of fare increases is going to give you the number of passengers. That fare increase means that they're taking 210 and increasing that. The cost of the flight is called a fare increase. Okay, so those are our functions or our expressions that we're going to use. Now what we're going to try and do is figure out what would be the total revenue for this flight based on the number of passengers and the price, right? That's how you determine the cost, the number of people flying times the cost for each person. So the number of people flying is 81 minus x, and the cost is 210 plus 3x. Distribution will give us negative 3x squared plus 33x plus quite a large value here, $17,010. So I just did that through distribution. Okay, now we're going to interpret this graph. The maximum revenue is going to occur at its maximum point. And since we're working with a parabola, a quadratic, it's going to be at the vertex. Because this is a sad parabola, you can tell that by the negative 3. So let's find our vertex. H is going to be the opposite of B divided by 2A. Negative 33 over 2 times negative 3, which is 5.5. That is our H value. That is the X of our vertex. And what did X represent? It's the number of increases to your fare, and each of those increases is $3. So the revenue would be your amount at, including, I should say, those increases. So if you take your calculator, you can figure that out pretty quickly. Ooh, I put a 7 right there. That is not correct. That should just be a 2, right? Sorry. Okay, so altogether, quite a large value here. We're looking at $17,175. So now let's interpret this for our airline company. The maximum revenue will be achieved with 5.5 increases of $3. So not a total, so we're looking at 5.5 increases of $3. That means that the cost per person, the fare cost, is 210 plus those $3 increases, 5.5 of them, which is $226.50. So quite an expensive flight, but I guess that is the maximum expense. If they went more than that, they would actually start to lose too many passengers, and it wouldn't benefit them. So now let's look at this third example together. We want to be able to look at data and try and determine, okay, these are all kind of scatter plots, but what kind of model would best fit them? Is it a linear model, a quadratic, or does it not fall into any of those? So looking at graph A, that first graph, that looks like, what do you guys think? Why don't you take a moment and try and figure out A, B, C, and D. Pause the video, write down your guesses, and see if you're correct. Okay, so let's reveal these answers. A is in fact a quadratic. Yeah, if we were to actually connect those points, it wouldn't really look like a true parabola, but it follows kind of that shape. B is actually a linear model. Yeah, they're not all in a straight line, but they're kind of following that straight increasing path. C is a quadratic as well. And D is none of the above. That is just truly a bunch of scattered points. Okay, one more example here. How do we find the equation of a parabola if we're given a point and its vertex? Okay, well, let me show you how that's done. We would use vertex form because we know the vertex. And we'd substitute in our values of h and k as well as our x and y. And that will leave only that little a. Be very careful that you change that 4 in your vertex, the x, to the opposite, right? Okay, so now that we have our equation, we're going to solve for a. I subtracted 6 on each side and simplified inside those parentheses. Negative 6 squared is 36. And then dividing, a is going to be a negative 1/4. All right, now we know a and we know the vertex. That allows us to substitute a, h, and k into our vertex form. So there's my a value, h, and k. And the problem asked us to write it in standard form. If it didn't specify, you could just leave it like that. But to write it in standard form, we have to have ax squared plus bx plus c. That means that inside of those parentheses, we're going to have to expand that by singing the song. Take the first term square it, take the second term square it, take the first times the second times 2. And that is now expanded. Then, as you are probably guessing, we need to distribute in that 1/4. And then you can combine those last 2 terms. And that would be our equation that goes through the given point and the also given vertex. So there you go. You have a whole lot of new processes that will allow you to solve problems and also determine your equations of your parabolas. Thanks, and we'll be practicing more.